Hello and welcome to the final chapter of the semester, particle physics. So, particle physics is uh the so what we've been doing through physics is getting more and more precise. So we start out with solids, we see that they're made out of molecules. We see that each molecule is made out of an atom, and each atom is made out of nuclides. Uh which are, it turns out, not even the smallest particles. So neutrons, protons aren't the smallest, are actually made up of smaller particles named quarks. So what we do is we try to find these fundamental particles and try to find these uh, more specific rules for how they interact, uh, or how they interact and how they occur. And then using that, we're going to, we don't have immediate ideals for how that knowledge is going to help us, but the knowledge that we've done, learning about electrons, learning about neutrons, uh, or learning about higher order particles has us seen throughout this course, of course, been very necessary. So I'm just going to talk a little bit about the types of particles that are smaller than neutrons and protons. And the electron itself is actually a fundamental particle as far as we can tell, but these particles uh, are governed by rules which hopefully someday will be useful, and uh, at the moment are increasing our knowledge of the world around us. So, there are four fundamental forces: the gravity, which has a relative strength of 10 to the negative 38, the weak nuclear force, which has a relative strength of 10 to the negative 13th, the electromagnetic nuclear force, which has a relative strength of the 10 to the negative 2, and the strong nuclear force, which has the relative strength of 1, where all of the relative strengths is just how strong the force between two particles is. Two protons is compared to the strong force. So gravity is actually really, really weak, but because gravity adds on with mass and doesn't cancel out with different types of charges like electromagnetic force does, or doesn't have such a small range like the weak and strong nuclear forces do, gravity is going to be one of the is going to become the larger force as mass gets bigger, as you have these huge, relatively neutrally charged uh, objects like the planets. So what we actually found, uh, we didn't know why a particle should, one particle uh, knows why another particle is there. So we don't know why there is action at a distance. We don't know why there is, why a neutron or a proton should know that there is another neutron or a proton a meter away. So Yukawa proposed that the nuclear force is actually transmitted through the exchange of particles, which were referred to as pions. And then there was further development where there was the ideal that electromagnetic force was mediated by another gauge particle, where a gauge particle is the name of a particle which mediates a force called the photon, which we've already talked about quite a bit. A photon is the particle of light. So these photons, when a positive particle is near a positive particle, it releases a photon, and then that photon causes the actual motion of the particle across against each other. So there are 4 fundamental forces, and there are 4 carrier particles: the graviton, the W and Z bosons, the photon, and the pi mesons, which are now called gluons. So the range of the graviton and the W and Z protons are infinite, but the range of the photon and the pi meson are rather small, and this comes down to the mass of the objects that are of the particles that are mediating. So a more massive particle will have a more massive have less range. So more massive particle range goes down according to mass, or according to the inverse of mass. So the way that we actually find these is something called particle accelerators, where we use the fact that E equals mc squared. We just put particles into a ring and keep accelerating them over and over again until we collide them. And then the energy that's released, as we have a proton and an antiproton. So the book, I don't think, really gets into what a matter and antimatter is. So basically matter and antimatter, or it does in a little bit, but it doesn't get into that now. But basically matter and antimatter, when they come together, annihilate and release a lot of energy. And that energy can be used to create new particles, which is why we have gigantic accelerators that are like the size of towns, built in, or maybe not the size of towns, maybe the size of a village, built in various research labs. And then what we found was that the proton and the neutron were actually made up of nucleon particles called quarks, which have different flavors and charges that add up to the charge of the composite particle, of the proton or the neutron. So these quarks have flavors, and they also have colors, where a color is like a charge for a quark and determines whether or not a composite particle is allowed. So color doesn't have anything to do with light. It's kind of just another property of matter, or property of these specific particles that determines what is and isn't allowed. And then this just goes into that a little bit. So special names are given to particles that feel the strong and weak nuclear forces. So all particles feel, except those that are massless, even those that are masses are affected by gravity, since gravity affects space and time. And all charged particles are affected by the electromagnetic force. But special names are given to particles that feel the strong and weak nuclear force, which are called hadrons and leptons. So hadrons are distinguishable by being able to feel both the strong and nuclear forces, and all particles feel the weak nuclear force. And then these are some examples of hadrons and baryons and lepton, or hadrons and baryons and leptons. So a lepton is an electron, a neutrino, a muon, and a neutron. Hadron is something like the pion or the eta, and then a hadron is something like the proton or the neutron, where the proton and the neutron, again, a lot are made up of quarks. And then baryons are, this is just, I'm not, so the chapter leaves out a lot of prescient details, but this is just, I'm just trying to get through the ideal of there being different types of particles, and that these particles are themselves composite particles. So proton and neutron, as I'm going to continue to focus on, a proton is an up, down, and up particle, and a neutron is an up, down, and down particle. So the charge of the proton is 2/3 plus 2/3, which are the charges of the up particles, minus 1/3, which means that it has a charge of 1, which means that it has the charge that's the same as the electron. And the neutron has a charge of 2/3 minus 1/3 minus 1/3, which is equal to 0, which is what we should expect. So antimatter is considered the opposite of matter. So I only studied antimatter very briefly, like maybe 20 minutes of one class in my education. But I think that antimatter comes from the fact that E equals mc squared. Also, yeah, the E equals mc squared, and all the equations that went into that are all the equations that or all the equations that went into relativity, and all the thought that didn't say anything about there not being a negative energy particle, but basically an antimatter is just the opposite of matter. For most antiparticles, this means that they share the same properties as their original particles with the exception of their charge. So if you look back here, it has a symbol for electron, and it also has a symbol for an anti-electron, which is called a positron, E+. And then you have muons, mu minus, and then anti-muons, which are mu plus. So antiparticles just exist for the same by the same token as regular particles do, except for some reason, which we're not sure of, there is significantly less antimatter in the world than there is regular matter. So we're not sure of why that is, because there isn't like a really good physical reason for that to happen. But basically, you have a particle, and then you have the antiparticle, which is the same particle with opposite charges, which doesn't really make sense for the neutron unless you consider it a composite particle, where the particles that make it up do have opposite charges, but they still end up adding up to 0. And then this, all of this information, all of this, all of this information comes into play as something called the Standard Model, where you have quarks, leptons, and gauge bosons, as well as the Higgs boson, which is something that gives particles mass. So hopefully that should be enough to whet your appetite a little bit. But that is going to be the end of the semester and the end of this class. So thank you very much for being with me and looking through all of these videos. And I will not see you again soon, but I am very grateful that you have been here. Thank you very much.